Swayam Prabha. Digital India. Educated India.
Now there is a small text, you read it carefully. So before you go to the read part. So in Jablonski diagram, we have discussed a few things, right? So basically Jablonski diagram tells you the basic photophysical aspects after the light absorption. Light means UV visible light. Okay, what confusion do you have? What are the questions that you have about Jablonski diagram? Each team can come up with one question. Take a minute, you talk to each other, generate one question about Jablonski diagram. Something that you want to clarify, something you want to learn, something you want to know more about it. So vibrational relaxation time is not given, the figure it is not given. VR is actually a process faster than IC. That happens very fast. So if you want to arrange VR also, VR comes first. Okay, that was their question. Computational chemistry to Jablonski diagram. So people can actually calculate. There are different computational techniques available to calculate the energies of this. So all these energies that we talk about S0, S1, S2, it's computer only. People can compute. If the electronic system is given, energies can be computed. So if it's an unknown system, you can compute it and then you can do the experiment to verify it. So computational chemistry can actually calculate the electronic energies in the Jablonski diagram and then take a UV visible absorption spectrum and see the spectrum is now matching with the theoretical calculations. So people normally do that in research. When they do the spectrum, they will explain the features of the spectrum based on the calculation. So this calculation will give you the energies basically. What other questions on Jablonski? Which country Jablonski was living? His full name is Alexander Jablonski. Find out. Go back and check Alexander Jablonski has a very interesting biography in the sense that he participated in World War I and World War II and still did some chemistry. So those countries, it was a mandate that you need to go for military service. I will not tell the country, you find out the country. Okay. What questions do you have on Jablonski diagram? Any doubts? Say why triplet state is lower than singlet state S1. T1 is lower than S1 in all Jablonski diagram. That is a general trend, right? Why? This is one question I expected that you will ask. What is S? Triplet is higher than? No, which triplet are talking about? Triplet is T1 singlet excited state is S1. So T1 is always lower than S1. In all Jablonski diagram, that's the way they draw, right? Yeah, so why? So relaxation, so for example, this is a non-radiative decay, right? So we can say that because there is a decay process, the energy is decreasing. That is one argument that you are trying to say, right? So another way of explaining based on the spin, we can think, okay? The spin is changing, right? So when the spin changes, spin has some connection with the energy. It is called exchange energy. There's a process called exchange energy. Roughly speaking, when these two electrons, when they are opposite in spin, they can come close. Pauli exclusion principle will not stop it, right? It can come close. But when they are parallel, they cannot come close. Now imagine a situation where these two electrons, which are orbitally separated, but spin is opposite, they come close. They can come close because spin is paired. When they come close, what will happen to the energy? Both electrons having what charge? Negative charge. So like charge, when they come close, it repel. So the repulsion energy increases. Whereas in the other case, they are parallel, they may not come close. So the repulsion energy term, when you calculate the energies of this electronic state, all electronic energy states are repulsion energy only. There is no attraction between electrons. So when you calculate the repulsive energies, energy of this repulsion is higher for S1 compared to T1. That's why T1 is having a lower energy than S1. So the way that you can imagine is, when you have a ground state, you go to a common excited state from which S1 is higher, T1 is lower, because of the difference in this repulsion energy. There are explanations why it is. So now there are research, recently people have found out molecules having T1 higher than S1. That's something happening very recently in the research level. Okay, inverted singlet stage. But normally if you take any textbook, this is situation. T1 will be lower than that of S1 because of this repulsion energy problem. What other questions about Jablonski? Only one team ask a question. Whatever may be the question, doesn't matter. Some of the answer I may know, sometimes I may not know, but that's okay. Okay, yeah. So this transition, right, S0 to T1. So that is an intersystem crossing. Spin flip is needed. So we say it's a forbidden transition. Means probability is less. It is still happening. It may be happening. But compared to S0 to S1, that probability will be very, very less. Because it's a spin forbidden transition. What other clarification, doubts? Okay, let us move to the next text. Steady state and time resolved studies. Just read it, then answer one question afterwards.
In some other words, phosphorescence is also, some people will say it is as delayed fluorescence. It is wrong, but what is that?
Right. So hold on, all teams. There is another question. Delayed fluorescence and phosphorescence, they are not the same. Okay. Delayed fluorescence is a phenomena. It's a fluorescence. That means it will be S1 to S0. Only thing is it is delayed. Now why it is delayed is the question. There are cases where this Jablonski diagram where delta E of S1 T1, the energy gap between S1 and T1 is very small. There are systems like that. So then what we can think of is, suppose this is S1 and this is T1. See, the gap is very less now. So some intersystem crossing happens, vibrational relaxation happens. Now T1 stays longer time, that we agreed, right? When it is staying there longer time, the thermal energy in the system is sufficient to populate back these vibration energy levels in the T1. Then you can see that some of them are isoenergetic. So what happens? It can go back to S1 and from S1 it can emit as fluorescence. So it is a fluorescence, but it take a D route. It first go to the T1, then come back to S1 and then emit. That process is called delayed fluorescence. Delayed fluorescence is a very important topic for OLEDs, organic light emitting diodes. OLED doesn't want a triplet state, it wants all the molecule to be in the S1 so that you get the complete emission from S1. So to do that, people are making molecules with having lower delta E between S1 and T1. So again, computation can help. You can design some molecule without preparing, you calculate the energy gap. Suppose it is very less, you prepare it and see. So that molecule will be suitable for OLED applications. Great. Now go ahead to the next reading part. Which case? Delayed means phosphorescence will not be there. If all of them are coming back, idellam simultaneously nadakkudu. So depends upon how much it is going back, phosphorescence will happen or not. Rotational to vibrational. Right. So there are maybe, suppose you give that much kind of an energy, this transition can, for example, vibration and electronic can get coupled, the way that you told rotation vibration. So vibration and electronic, if it is coupled, it's called vibronic transition. So that involves both electronic energy levels and vibration energy levels. So like that, rotation and vibration can also be coupled. Like the Jablonski diagram is mostly for electronic. We are not worried about the rotation part here because we shine UV and visible light. That one only electronically excite. Rotation venana, you need to go to microwave. A corresponding energy. So people normally do is they don't want to couple this transition. They just give microwave so that rotationally it get excited. IR na vibrationally it excite. UV visible na mostly electronic. So they separate it to study that. Jablonski, because it is UV visible, we don't talk about this rotation part and all. Next job is a bit difficult, huh? All jobs are difficult. ஒரு கம்பவுண்ட் தான் இருக்கலாம். அது எஃபிஷியன்சி சேஞ்ச் பண்ணும். பிகாஸ் இது வந்து see you're putting a water tank, you just imagine, put some holes, வாட்டர் ஃபில் பண்ணிட்டு எல்லா ஹோல்லையும் வாட்டர் வரல, அந்த மாதிரி இதெல்லாம் சைமல்டேனியஸாக நடக்க பண்ணும். யூ எக்ஸைட் இட், இட் கேன் கம் த்ரூ டிஃப்ரெண்ட் சேனல்ஸ். ஸோ ஃப்ளோரசன்ஸ் வரும், ஃபாஸ்பரசன்ஸ் வரும். Depends upon the efficiency of this process. Some will be more fluorescing, some will be more phosphorescence. That's all. How is it going here? This all aromatic hydrocarbons, they're all fluorescing, like anthracene, naphthalene, adella. Phosphorescence molecules are relatively less. At the room temperature, we cannot actually see phosphorescence. As you said, the phosphorescence lifetime is high. Normally, room temperature, fluorescence is mostly visible. Phosphorescence, they say it will get quenched. So tomorrow we'll talk about quenching. There's a phenomena called quenching. We'll discuss that tomorrow. Photosensitizer is something that absorbs the energy from a light source and then transfer into another molecule. It basically sensitizes the excitation process. Quenching means fluorescence intensity reduce one. Any process that reduces the fluorescence intensity is called quenching. So adanaala phosphorescence will get easily quenched compared to fluorescence. And reasons irukku. So we'll discuss that tomorrow. Okay, so what is the question? Sketch a steady state emission spectrum and a time resolved emission spectrum. So what is steady state and what is time resolved is given in the text. Now using that information, you need to make an attempt. Take another minute, think about it. All information needed are given. You are drawn? Draw it. Just sketch it, how it looks like. So normally intensity can be on the y-axis. You can plot intensity on the y-axis. Emission intensity. So in the text they say no emission intensity. No, first you draw, then only we'll discuss. You discuss and draw. How to draw you discuss, then you draw. Yeah, sample light source detector, that's another layout. That's called instrument layout. This spectrum is what is asked. Okay. Any figure? Okay. Okay, time. Okay. So what was, how do you, like, what were your thoughts to plot that? Both. You're guessing something, right? What are your guesses? Steady state mean there will be a lamp always on. So this excitation process is happening all the time. So after some time, what happens that concentration of that excited state S1 will be constant. അത് പോപ്പുലേറ്റ് ആയിട്ടേ ഇരിക്കും. Whatever S1 is forming, it is coming back. And because lamp is always on, you have a steady concentration of S1. So suppose you plot concentration of S1, then it becomes cell level, not intensity. That's what we need to discuss. So intensity is basically the amount of photon that is coming from the S1. You have a steady concentration. Okay. So now what are you plotting on the x-axis? What are you plotting? No. In the steady state, what is the wavelength? So 300, 400, 500 nanometer changes. Then what happened to the emission? So you may be exciting 300 means probably S0 to S2, 500 means S0 to S1. So different excitation is happening. Adella steady state varum. So how the emission process as a function of lambda will change? That's a question. Time is separate. No, that's a time resolved experiment. First we'll see the steady state spectrum. Why do you cross it? That's okay. That's the second one, no? But why did you cross it? So maybe you can plot the time resolved spectrum because some clue is given in the text. Time resolved spectrum, there is a clue given in the text. You can carefully read it. Intensity versus time. Got it? So you have to assume that intensity we are starting when the excited state is populated. T0 means that energy state is populated. S1 is completely populated, then only clock starts. In the time resolved experiment, T is equal to 0 means excited energy is completely populated. Now it starts emission. So how the intensity varies? That's the question. And direct answer is given there. Read the text again for the time resolved. Did you read the text?
Yes.
Okay. So time resolved, what clue it is giving? So what is it? So it gives a clue, right? The time resolved spectrum follows first order kinetics. You learn chemical kinetics? So first order kinetic equation, same thing. First order kinetics have only some same behavior. Whether it is ground state kinetics, excited state kinetics. So how the first order kinetics graph, if you remember, and same thing will be. But that is not first order kinetics. That is zero order. kinetics. So chemical kinetics you need to refresh. There are zero order kinetic graphs, first order, second order, how the as a function of chemical kinetics means what? Concentration as a function of time. Here intensity as a function of time. Concentration and intensity as proportional. More concentration means higher intensity. Same thing. So if you remember a chemical kinetic CT plot, we call it CT plot, concentration versus time. If you remember CT plot of first order kinetics, same thing for intensity versus time for time resolved. Plotted? So that is corresponding to zero order kinetics. Intensity decrease, that part is clear. Intensity decreases like concentration decreases because it is coming down. Whether it is decreasing linearly or non-linearly is the only question. Linearly for the zero order. With a zero order kinetics, concentration with respect to time is a linear function. Its concentration will simply decrease for a zero order reaction. For a first order reaction, it's an exponential decay. Okay, first order kinetics, the moment first order kinetics, you need to remember that it is a exponential decay. Exponential means what? What is the meaning of exponential? Something is decaying exponentially means what? It's a lot of terminologies, but the meaning, physical meaning we need to get. Linearly decreasing, exponentially decreasing. What is the difference? Which is a faster way of decreasing? Exponentially. But then what case you say exponential decrease? Have you heard about T half? What is T half? Half time. Half time is what? How do you define half time? Okay, so this is all chemical kinetics part. In photophysics, we use a lot of kinetics because these are all processes, right? I told you in the beginning, molecule will not have any problem. But there will be several processes, molecule will be going from one state to another state. All these processes has rates. So rate equations you can develop, you can study the kinetics, dynamics of the excited state. So the whole entire photophysical research is to understand the dynamics, the rates of these processes, how to control it, so that we can use it for some purpose. That is the idea. Okay, so this is the graph for a time resolved fluorescence or phosphorescence spectrum. Okay. So this time will be in nanosecond for fluorescence, okay, like 1 nanosecond, 2 nanosecond, etc. So now the question is, see, when we say we told T1 is staying longer, the lifetime of T1 is higher than lifetime of S1, etc., etc. Right? Now we are in great danger because let us say a molecule's singular state lifetime S1 is 5 nanoseconds. Just assume that some time will be there, 5 nanoseconds. Now you are plotting a time resolved plot where intensity of the emission is changing as a function of time. 0, 1, 2, 3, 4, 5. Exponentially decreasing graph when the graph will touch the x-axis. In an exponential, for that you need to remember the equation of the exponential graph. Remember this equation? Concentration of A is equal to A0 into e to the power of minus kT. This is the first order kinetic equation. Okay. So E stands for the exponential decrease. Every equal time, equal amount decreases. That's called exponential decay means. That's why it's a faster decay. K is the rate constant. T is the time. This is a normal chemical kinetic equation. So if you want to make an analog to this, we can write intensity is equal to initial intensity e to the minus K into T. That K will be the rate constant for fluorescence, phosphorescence, what is the process that you are looking. And I can also write instead of K, T by tau, because K is 1 by tau. So any K is inverse of the lifetime, right? So I can write as I is equal to I0 e to the power of minus T by tau. Now the problem is, if you look at the exponential equation, the I becomes 0 or this A becomes 0 only when T becomes infinity. This will be decreasing, but it will not touch. It will just go asymptotically, decreasing, but it will touch that line only at infinity. In other words, now we have a difficult situation. The molecule is coming down to the ground state not at one particular time. It's keep on coming down. Only thing is more molecules are coming in the beginning time, less number is coming afterwards. That's why intensity is coming down. But molecules are keep coming. So how do I say one time as a lifetime? People report no, lifetime is 5 nanosecond, 10 nanosecond, 100 nanosecond. How is it possible? Because I am getting decay at 1 nanosecond, 2 nanosecond, 3 nanosecond, 5 nanosecond. Infinity also theoretically something is decaying. So when you have multiple numbers, you need to narrow down to one number. What is the solution in science? You have different heights in a classroom, but you want to represent one height as a representation of the classroom. What do? Same thing. So lifetime that is reported for molecules, 5 nanosecond, 10 nanosecond, it doesn't mean that that particular time molecule is coming down. Molecule is coming down all the time. You take the average time. That time is called the lifetime of that molecule, excited state lifetime. So lifetime in photophysical studies is a very extremely complex concept. Because of this phenomena, it can come at any time. It's just a probability distribution. Probability decreases as a function of time. So instead of telling one time as the lifetime, you take the average of that lifetime. And that average is normally taken as, see for example, if you want to say T is equal to tau, the lifetime, the time taken for the lifetime, then this becomes I is equal to I0 by E, or 1 by E of initial concentration. So the intensity, the time taken to reach the intensity which is equal to 1 by E of the initial intensity is taken as the lifetime. That is only the way that you can define lifetime. Because of this situation where every time it is emitting. Okay. Now coming to the steady state. I know this is slightly confusing. This time resolved spectrum is difficult, but at least you can imagine that the lifetime concept, we need an averaging aspect because not a single time the molecule is coming down. Many times the molecules are coming down, so you need to average it to report the lifetime of a molecule, excited state lifetime. What is not clear? What is unclear? What are your doubts? because several students think that when you have 5 nanosecond, 10 nanosecond, I normally ask in the classroom, even in IIT. So 10 nanosecond, they think that after 10 nanosecond, all the molecules are coming down. That is incorrect. Okay, 10 nanosecond is the average time that the molecule is staying, or we can say that is equivalent to the time taken for intensity to reach 1 by E of the initial intensity. Some 67% time for 67% to come down. That is the idea. That is the only way we can define it. Why? Because it is coming all the time. Keep on coming. You don't have a control on that. Okay? Alright. Read the last text for today's class. The other plot we did not plot, no? Steady state. Intensity versus lambda. So, lambda means wavelength. That is the wavelength of the light that is emitting. So, imagine that you are exciting to some S2 or S3 or something. It keeps coming to S1 and then it is emitting. But S1 also, you can see that it can emit to this vibration level, this can emit to this vibration level, this can emit to this vibration level, this can emit to this vibration level. Now the energies are different, right? So the intensity of each of these transition can be different. It cannot be the same thing. So when the energy change means lambda change. How lambda is connected with energy? Inversely proportional. High lambda means lower energy. So the energy decreases means lambda changes. So if you are plotting a lambda versus I, you know that there are different transitions with the different energies that will be reflected in the steady state spectrum. So your intensity will be varying, depends upon your lambda. Something like you will get it. Vary from molecule to molecule. Different lambda, you may have higher intensity, lower intensity, but you get basically an envelope or a broad band for each of these transitions. Now there can be other questions. I draw a straight line which is having a definite one energy, right? So I am supposed to get like this. Why am I getting a broad peak instead of just one line? Because this one transition is one energy, one lambda. So I am supposed to get only one lines in that spectrum, but so that I am getting a broad peak. So that is called spectral broadening. There are other reasons for that. Okay, why you can find out why spectral broadening happens in spectroscopy or in emission spectra. You can just Google it, or you can ask ChatGPT. It will tell you why spectral broadening happens. But essential thing is that depends upon the lambda, the intensity changes. That is a message of steady state spectrum. Time resolved spectrum follow first order kinetics. Okay, now read the last paragraph. So when you read the text, if it's something is not clear, you need to ask me.
Which state the electronic transition can be decoupled from nuclear?
What's the meaning of that? So that's the first question. Like in theoretical, when they make the theoretical framework, they say that the time taken for electronic transition, the time taken for nuclear movement, they say that you don't have to connect them. You can decouple it. So the question is, what is the logic of that assumption? So you are taking time for electronic transitions, and nucleus of these molecules also move, right? But they say that these time scales no need to connect. Why do you think they argue like that? So that depends upon how much energy you are giving. So they say that, but these electronic transitions are independent of the nuclear movement, nucleus of the molecular system. Okay, but this is only process where nucleus is moving and electron is moving. Nothing is happening to the nucleus. Random process, that photophysical process. And now why they said it is not need to couple? Why do you think so? So just compare some properties of electrons and the nucleus. And moving means, how does what properties do you think we need to consider when something is moving? See. So now you compare which one is an electron versus a nucleus. Nucleus என்னெல்லாம் இருக்குது? Mass ரொம்ப அதிகம். So the a heavy mass moving, a lighter one moving. Lighter one doesn't, you can disconnect it, because by the time this moves, this can go many times. So that is the basic assumption, Frank quantum principle saying that, or we can also get Born Oppenheimer approximation. So that these things you can decouple. Okay. So decoupling is the electronic transitions and the nuclear movement. These times you don't have to couple. You can consider them as two. One is not depending on the other. So the first question is, what is the logical reason? Why do they say like that? Okay. Okay, decoupling. Decoupling means the electronic transitions and the nuclear movement. So what they are saying is that you don't have to consider them together. They are rather independent. Something is, both are moving, but electronic transitions don't have to consider the nuclear movement. What is the logic behind that assumption is the question, first question. Decoupling is confusing. Decoupling is simple. In the sense that there is nuclear movement, electronic movement, and the nuclear movement. They say that they are rather independent. One is not depending on the other one. So you can decouple it. The first question is, what is the logic behind that argument? So what is the logic behind decoupling the electronic transition from the nuclear movement? See, both are movements. So what they are saying that they are rather independent. Then what is the logic behind that argument? Something is moving, two things are moving. Now they are saying that you have to consider them, you can consider them independently. So when something is moving, what are the parameters that comes to your mind? So electron is moving, nucleus is moving, but when you compare these two things, something striking saying that, okay, this movement is totally different, or it may have some other. When something is moving, what parameter do you, A and B are moving? Force is one thing, but here there is no force externally happening. What other things? Photons coming, but photons are energy providers. It provides the energy to the electron. That's why it's moving. Nucleus also moving because there is a translational movement. But they say that these two things are rather independent. So, what is the first question answer that your team is thinking? Any idea comes to your mind? Okay, so from your team, what is the answer that you have given? For the first question, the reason why electronic transition and nuclear motions can be decoupled? Mass of the electron and mass of the nucleus. Which is a lighter particle? Electron is much lighter than nucleus. So that movement, by the time the nucleus moves, electron can move many times, or these movements have different time scales. So when you are talking about electronic transition, no need to worry about nuclear movement, because mass is very high, heavy. That is the reason, that is a logical reason why they decouple these two things. So in the electronic transition, you can basically just represent them as a straight line in potential energy diagram and all. You know potential energy diagram? Energy versus reaction coordinates or internuclear distance. So such kind of plot, you can actually represent the electronic transition as a straight line, because internuclear distance remains the same. Nucleus is a heavy mass, so it doesn't move when the electrons are getting excited. So that's the idea of decoupling. Okay. So now we don't have much time, we have only 2 minutes. We'll stop at now. Okay. We'll continue the same thing and more tomorrow. But what I want is, you need to fill this each team. Okay, when you come back tomorrow, up to this question you can fill it properly, whatever the discussion. Each team take one leader, one person as a leader. Whom want to choose as one person responsibility? Just decide among yourself. Whom wants to take? Okay, your name was Uma. So Uma can be team leader here, there. Just tell the team leader's name. Bhuvaneshwari is the team leader. Here Dhanalakshmi is the leader. Here Devika, what's your name? Devika. Devika can be the leader. Here, Iveda can be here. Mohanlal can be. Leader doesn't need anything. Only thing is to collect the information. Make sure that when you submit, also give a team name. You choose a name for your team. Write it on that one and submit tomorrow when you come. Okay. So I will see you tomorrow at 9 o'clock.
SwayamPrabha. Digital India. Educated India.